Alright, so let's take a look at the preparation for our final exam. From Skill 1, if we go back to it, we're looking at complex numbers. So before we jump in and start doing some of these problems, let's review a little bit of things that you should immediately think of when you hear complex numbers. How we defined a complex number, we defined that the square root of -1 is equal to I. And I is referred to as the imaginary unit. Sometimes you will have textbooks that will define -1 to equal I squared, and they have just squared each side. So it really is not going to create any problems for us. It is true that I squared is equal to -1, but we're going to have as our standard definition that the square root of -1 is equal to I, and we call I the imaginary unit. When you're asked to simplify an expression or to write your answer, they typically want it in standard form. The standard form of a complex number is written as a plus bi. The first term a is referred to as the real part of this complex number. The second term has two factors, and the factor b is the imaginary part, and like we said, I is the imaginary unit. It is often very useful for us to plot points that represent complex numbers. We can use the rectangular coordinate system and plot x comma y if we just use the x-axis for the real part to plot A and the y-axis for B. So if you had a complex number 3 plus 2i and you were plotting it on a rectangular coordinate system, you would plot the point 3 comma 2 from the origin, go to the right 3 places, and then up 2. At times, we'll be asked to find the absolute value of a complex number. Written in standard form, the absolute value of a plus bi, they're asking you to calculate the distance from the origin. The origin is at the point 0, 0. Our point of interest is a comma b. Using the distance formula or using the Pythagorean theorem, you can show that the absolute value of a plus bi is equal to the square root of a squared plus b squared. Notice that there's no I in this formula. This represents a distance between 2 points, and we do not use this imaginary unit to represent distance. Oftentimes, especially with division of complex numbers, we are interested in the conjugate of a complex number. So the conjugate of a plus bi is defined to be a minus bi. Notice that the real parts are the same, but the imaginary part is equal and opposite. When you are multiplying complex numbers together and it's a conjugate, you don't necessarily have to create a table if you realize that suppose we did create a table. Suppose we did have a plus bi and a minus bi, and we used a table. A times a was a squared. Notice that a times negative bi is negative abi, and a times bi is positive abi. That this diagonal, that these terms cancel each other out. Bi times a negative bi is a negative bi squared, but remember that I squared is -1. So you have a negative times a negative, and along this diagonal, it's a squared plus b squared. So you're going to save yourself a lot of time if you recognize when you're multiplying conjugates together that it's just a squared plus b squared, rather than doing your table. So let's jump in and do some problems. Here they're asking us to simplify this, so they want our final answer to be in standard form of a plus bi. We're going to treat these like we did when we learned like terms and unlike terms. For the real part, we're going to come in and add these real parts together. We've got 6 plus 5 and then minus 9. That's going to be the real part of our complex number. And we've got a negative 4i minus a 1i minus 5i. So if we combine these, 6 plus 5 is 11. 11 minus 9 is 2. Negative 4i minus 1i is negative 5i. and then another negative 5i is minus 10i. And you don't have to put plus a minus 10i. We do relax a little bit in the standard form, and we do accept that you can write it as subtraction. But the real part A is equal to 2. The imaginary part B is equal to negative 10. And this is written in standard form of A plus BI. Alright, so let's move on. They ask us now to simplify this product. I don't have complex conjugates, so one organized way for me to multiply these values together is to use a table. We're going to use the distributive property. I've got 5 plus 2i. I've got 1 minus 3i. Doesn't matter whether I wrote the 1 minus 3i on the side and the 5 and 2i across the top. That doesn't matter. 5 times 1 is 5. 1 times 2i is 2i. The 5 times negative 15i. And here I have a negative 6i squared. Now remember that I can rewrite this negative 6i squared as negative 6 times a negative 1 and see that as a positive 6. So this product, along this diagonal, I just have 5 plus 6, which is 11. And along this diagonal, I have negative 15i plus 2i, which is a negative 13i. So when you multiply these two complex numbers together that they gave us originally, that's what you should get. That's our final answer. Now here I don't necessarily have to construct a table if I recognize that 7 plus 2i and 7 minus 2i are complex conjugates. And remember, if you have a plus bi times a minus bi, it's a squared plus b squared. It's 7 squared plus 2 squared. 49 plus 4, 53. And I could move on much quicker if you recognize that you can use that formula. Now here you must be careful that 6 plus 5i quantity squared does mean 6 plus 5i times another 6 plus 5i. Exponents do not distribute. This is not equal to 6 squared plus 5i squared. Exponents don't distribute. You'll be losing that middle term. So if you write it out, what this exponent means is repeated multiplication. And if we form a table, because I don't have conjugates here, I have 6 plus 5i. I have 6 plus 5i. 6 times 6 is 36. I have a 30i for that product, a 30i for this, and a 25i squared, which I know since I squared can be replaced with negative 1, that this is a negative 25. So, along this diagonal, I have 36 minus 25, which I think is 11. And along this diagonal, I have 30i plus another 30i, which is 60i. So there's our final answer. Be careful, exponents don't distribute. Alright, so here I've included a little graph for you to think about, because if they're asking me to calculate the absolute value of 2 plus 7i, let's come in and plot the point 2 comma 7. If I go to the right 2 and up 7, I'll be up here. So what they're asking me to do is to find the length from of this line segment from the origin up to my point. Well, like I say, you can try to memorize the distance formula, or you can try to recall the Pythagorean theorem, but if you recall, one of those things that you want to have committed to memory is that if you have the absolute value of a plus bi, that it's equal to the square root of a squared plus b squared. Now, don't get this formula mixed up with the product of the complex conjugates. It's just coincidence that happens to be a squared plus b squared. So, let's come in here. If a is 2 and b is 7, notice I don't have an I for a distance. They're asking me for the length of this blue line segment from the origin to that point of interest. So 2 squared is 4. 7 squared is 49. 4 plus 49 is 53. And I can't simplify the square root of 53. They do expect us to simplify radicals and to give exact answers. Don't approximate that on a calculator. Just give that square root of 53 as your answer. All right, our final set here on this skill packet 1 for complex numbers is division. We actually use multiplication to find division. When it says simplify, they want our final answer in that standard form of a plus bi. So what we're going to do is multiply this number by the number 1. But we're going to be clever in how we write the number 1. We're going to use the complex conjugate of the denominator. Never of the numerator, but of the denominator. So we're going to multiply by 2 minus 3i. Since we want this number to be 1, the numerator and denominator are equal to each other, because now that would just cancel to the value of 1. Alright, in the denominator, I don't have to create a table and spend much thought. If I have a plus bi times a minus bi, I know it's a squared plus b squared. 4 plus 9, I know my denominator is 13. Now, I am going to have to take a little bit of time and effort to calculate the 5 minus I times 2 minus 3i. I don't have any shortcuts to speak of for it. However you prefer to multiply binomials. I suggest for most of you to use a table because it's an organized way for the distributive property. But if you have a different way that you spell out FOIL, or you've memorized some other pattern, that is fine. So if I multiply here to get my entries, we've done this enough times, I believe it's pretty obvious how I'm getting these values. Negative times negative is positive, but I squared, that's a negative 1, so that's going to make this a negative 3. So along this diagonal, I have 10 minus 3. Well, 10 minus 3 is 7. And along this diagonal, I have a negative 2i and another negative 15i for negative 17i. And this is being divided by 13. Now, I don't have a problem if you leave your answer like that. But remember, if they're asking us for a plus bi, the a of this is the fraction 7 over 13. And the b is negative 17 over 13 times I. So this part is a, this part is b, this factor is your imaginary unit I. So we've written it of the form a plus bi. Whoops, I have an extra negative sign there. So I guess I am technically writing it here in the a plus bi form. Like I say, oftentimes you'll see people write it 7 over 13 minus 17 over 13, and they'll just include that negative sign when they identify their imaginary part. Hope this helps, and I'll continue making these videos with the rest of the review problems. I will talk to you later. Bye.